Good morning, welcome to Physics Studio. What we're going to talk about today to finish up our unit on magnetism and electromagnetism is something called a generator. And I think you already have a pretty good general idea what it is. But let's take a look. Now, there's a characteristic of the physical world that, which we might call symmetry, that means that there's a lot of processes that can be run both forwards and backwards. So for example, you can have evaporation and condensation. Those are the reverse of each other and they indicate a deep relation between heat and kinetic energy. You can have things freeze, you can have them melt, etc. A lot of processes operate that way. So we know that a motor converts electric energy to mechanical energy or work. And we've seen how that's done. We need to have a rotating element that we call a rotor. We need to have a fixed housing. So that the magnetic objects produced can exert a force on each other. And we need magnets. So for example, we can have an electric source like this. You could say that we need a power source too. And you could have your rotating element like this. And we could fix magnets to it, alternating the polarity. And by swapping the direction of the current, we can cause this to be sometimes a north pole and then switch to a south pole. And you can see right here that if this is a north pole, it's going to push that north pole away and pull this one. And so we need this fourth element in a motor, because once that south pole gets over top of the north pole right there, if we can switch the direction of the current right then, this will turn to a south pole and push this away and pull the next one. You know, just like on the merry-go-round where you pull and then push. And so the device that swaps that direction of current, thereby swapping the polarity at exactly the right time, sometimes thousands of times a minute, is called a commutator. Now, there's other ways you can get this configuration. You can have on your fixed housing magnets, right? So this would be a north pole and a south pole, giving us a magnetic field. And you could make your rotating element the coil of wire. And if you have it configured like this, it will be turned this way. Once it gets right to here, if you can switch the polarity, switch the direction of current, it'll then be pulled again, and you can get continuous motion. Either way, you've got a rotor, rotating element, a fixed housing, you have magnets, and you need that commutator to switch it just the right time. So that's how the motor works, but by symmetry, we would expect if we have a device that converts electrical energy to mechanical, we would expect there to be a device that converts mechanical energy to electricity. And of course there is, and it's called the generator. And the generator's operation is pretty simple. You still need the rotor and the fixed housing and the magnets, but you don't need a commutator for a generator. Now, let's take a look how that works. Now, to understand this first, we need to understand a concept called magnetic flux, or phi. Phi is just another Greek letter. And magnetic flux is an indication of how many field lines you've grasped of a magnetic field. So say you have a magnetic field. Say that magnetic field is going into the page like that. Call that B. And we have a wire of some sort, like in a circle, and it's captured 3 field lines. Right? Now, there's a number of ways we could change the number of field lines being captured. We could increase the strength of the field. Right? And then we would get more. We could increase the area of that. And we could also change the angle. And let me show you what I mean by that. Okay, let's say that we have, I want you to imagine that this is a hula hoop and I'm standing in the rain. Okay? And if I hold the hula hoop like this, a certain amount of rain is going to fall through that. That would be the flux, right? And we can increase the amount of rain being caught by this by increasing the area of the hoop. Also, we would get more rain if it was raining harder. But another thing we can do is we can turn this at an angle, right? So it's getting a maximum amount of flux right now. As we turn it, it gets less and less and less, and then at this point right here, it's getting 0 flux, right? Even though it's the same area, right? And if we continue doing this, we'll get a constantly changing flux. And what we found, and this is a little weird, but what can induce a current in a wire or a loop of wire is not a magnetic field itself, but a change in the magnetic field. And that's the purport of the little simulation that we did today. If you remember, with our simulation, if we have a magnet here, right, this magnet right here, and it's sitting inside a loop of wire, nothing happens to the current, right? We have this hooked up to a little device and then a voltmeter. But if we take this and move it, suddenly current occurs, right? Notice that it's catching a lot of field lines right now, right? A lot of flux. We pull it away out here, it's not catching much. But we can still get that current, small amounts of current, by changing that. Now, if we take that, do that repeatedly, what you can see is we'll get an alternating current. And if we switch the side, notice when I push the north end in, we get a negative current, out produces positive. If we swap the polarity, in produces positive and out produces negative. And so what's happening there is that by physically moving the magnet, around the coil of wire, we're causing the magnetic field B to fluctuate between a north and south pole, right? And so if we take the north pole and press it in and out, we're getting a high north, a strong northern field. Then it drops down somewhere to 0, and then we push it back in, strong north, like that. And if we switch the polarity and make the south end, put the south end of the magnet into the coil, then pull it back out, push it back in, then we'll get something like a fluctuating magnetic field B like that. And what you can see is that what we're producing is an alternating current. And we don't need a commutator because we're controlling the frequency of that process. Now I want you to watch one more thing real quick. If we take the magnet and place it inside there, right, now we have zero current because it's not moving. But if we start swapping the polarity, watch what happens. Right, we're getting way more current right now. And so what's happened in that case is that we were swapping the polarity of the magnetic field inside the coil, right, making it go from north all the way to south, all the way back up to north, all the way back up to south. So we're getting a much larger swing in the strength of the magnetic field, which produces more current. And so what's happening is that change in the magnetic field, the change in the flux, produces an EMF in the coil that drives current. An EMF just means voltage. Now, there's another way we can do that, right? Instead of physically moving the magnet around, what if we fix the magnet into place? And we're going to take a look at an image from your textbook. This is chapter 23.2, page 828, and it's image 23.11. And what you see here is we have a fixed magnet here with the North Pole pointing in and a fixed magnet here with the South Pole pointing in. And we have a loop of wire that is free to rotate. So we've got our magnetic field going from north to south here, right? And that's fixed and unchanging. Now, if we give some mechanical input, and that could be from water falling in a hydroelectric dam, it could be wind in a windmill, it could be you cranking something by hand. If we input mechanical energy like that, that's going to cause this to turn. And what that's going to do, like with our hula hoop, as this turns, that flux is going to go to 0 to maximum, to 0 to maximum. And we can turn that, as fast as we turn that, we're going to get more current. So what happens there is by turning that, you're causing this constant magnetic field to be, a constantly differing amount of this field to be captured by this, which then produces an EMF or a voltage, a potential difference, which then drives current through this. And as long as you keep that turning, that will continue to produce current. Now, the only trick is, and this is really complicated and you won't be responsible for this, as you turn that loop of wire through the field, it produces a force, right? Because we know that a current carrying wire will produce a force. That force is produced against the direction you're cranking, so that if you actually have a generator, you'll feel the resistance as you produce the current. Because, of course, you can never get something for nothing. So anyway, I hope that helps you understand how the generator works. Don't worry about the formulas for magnetic flux. Just approach 23.1 conceptually. And let me know in the discussion board what sort of questions you have. Have a great day.